A racing yacht rolls over in the South Pacific and stays upside down. The skipper is alive inside the hull, in the dark, above her own ceiling. No helicopter on Earth can reach her. She is out where Point Nemo lies, the spot in the ocean farthest from any land, roughly 2,688 kilometers from the nearest scrap of shore. The first answer sounds obvious. It is simply too far. That answer is wrong. We hit this exact place on purpose, repeatedly with falling spacecraft. So why can we aim at it and not survive it? That contradiction is the whole story, and it is stranger than it sounds. Because Point Nemo is not a place anyone found. It is a place someone calculated. In 1992, a Croatian-Canadian survey engineer named Hrvoje Lukatela ran a geospatial computation to solve a very specific question. Where on the ocean is the point that maximizes the distance to the nearest coastline? Not the deepest water, not the emptiest water, the farthest water. He was using his own geodetic software, working on an ellipsoidal model of the Earth rather than a flat chart, because on a flat chart, the answer comes out wrong. The result was a coordinate: 48 degrees 52.6 minutes south, 123 degrees 23.6 minutes west. Nothing is there. That absence is the point. There is no rock, no shoal, no buoy, no marker, no discoloration in the water. If you sailed across it and your instruments failed, you would never know you had been there. What defines it is not what it contains, but what it is far from. And the geometry of that is oddly beautiful. 3 pieces of land sit almost exactly the same distance away, forming a triangle with Point Nemo at its center. To the north, Ducie Island, an uninhabited coral atoll, at the far eastern end of the Pitcairn Group. To the northeast, Motunui, a rocky islet off the southwestern tip of Rapa Nui, better known as Easter Island. To the south, Mahair Island, a lump of volcanic rock off the coast of Marie Byrd Land in Antarctica, locked in ice for most of the year. None of those 3 is a refuge. Ducie has no fresh water and no permanent population. Motunui is a bird islet with cliffs, not a harbor. Mahair Island is Antarctica. So the number that gets quoted, that famous 2,688 kilometers, is worse than it sounds, because it measures the distance to the nearest land rather than the distance to the nearest help. The nearest land will not treat your broken leg, will not give you fuel, will not answer a radio call. Reaching it does not solve anything. It only stops the water. Start with the obvious question, because it is the one that traps most people. If there is nothing out there, why is it hard? Emptiness sounds like the absence of hazards. No reefs to hit, no traffic to avoid, no coastline to be driven onto in a gale. On paper, the safest water in the world should be the water with nothing in it. The reason that reasoning collapses has to do with why the water is empty in the first place, and that begins in the atmosphere. Point Nemo sits inside the South Pacific Gyre, the largest of the ocean's 5 great rotating systems, a slow wheel of water thousands of kilometers across, driven by the trade winds on its northern edge and the westerlies on its southern edge, and turning anti-clockwise in the southern hemisphere. Above the middle of that wheel sits a persistent zone of high atmospheric pressure. Air descends there, warms as it sinks, and suppresses cloud formation. The surface water beneath it is pushed inward from all sides by the wind stress and the Earth's rotation, and it piles up very slightly in the center, a mound of water perhaps a meter higher than its surroundings, spread over an area larger than any continent. That mound has a consequence that decides everything else. Water pushed inward and downward means water that does not rise. Along the coast of Chile and Peru, wind drags surface water offshore and cold. Nutrient-loaded water climbs up from the deep to replace it, which is why those waters carry some of the densest fish populations on the planet. In the middle of the South Pacific Gyre, the opposite happens. The nutrients that sink out of the sunlit layer never come back. Nitrate and phosphate and iron drop into the dark and stay there. What is left at the surface is warm, stratified, transparent, and starved. So the emptiness is not an accident of geography. It is manufactured continuously by the wind. And it cascades outward into every human decision anyone has ever tried to make out there. No nutrients means no plankton. No plankton means no fish. No fish means no fishing fleet. No fishing fleet means no vessels wandering across that water for commercial reasons, which means that when something goes wrong, there is nobody within 1,000 kilometers who happens to be nearby. Now add the second layer, which is about routes. Ships do not travel in straight lines on a map. They travel on great circles, the shortest paths across a sphere, and the great circles that matter in the Pacific all bend away from this place. A ship running from Panama to Auckland cuts across the tropics. A ship from Valparaiso to Sydney runs west and slightly south, but stays well north of the 50s. A ship rounding Cape Horn for Asia climbs north as fast as it can. To pass close to Point Nemo, you would have to deliberately steer into the middle of a triangle of nothing, adding days of fuel and days of crew time, for no cargo, no port, and no reason. Commercial shipping is a business of margins measured in fractions of a cent per ton-mile, and there is no margin in going there. The United States Coast Guard runs a voluntary system called AMVER, in which merchant vessels report their positions and intended tracks, so that a rescue coordination center can find out, within minutes, which ships lie near a casualty. It has been operating since 1958 and covers tens of thousands of ships. Plot the daily AMVER density on a world map, and you see the arteries of global trade drawn in light. The North Atlantic, the Malacca Strait, the Panama and Suez approaches, the routes along the Chinese coast. You also see a hole. There is a region of the South Pacific where the plot is effectively blank, and Point Nemo sits inside it. That blankness is not a graphical artifact. It is the answer to the question of who comes for you. Then, there are the cables. Almost all intercontinental data now moves through fiber optic lines lying on the seabed, and those lines are laid where the customers are. There is no cable running near Point Nemo, which means there is no cable ship patrolling nearby, no repair depot within reach, no industrial reason for anyone to keep a specialized vessel on standby in that quadrant of the Pacific. In the North Atlantic, a cable break brings a repair ship within days because the ships are pre-positioned and the money is enormous. In the South Pacific Gyre, there is nothing to break and therefore nobody stationed to fix it. Even the robots thin out. The Argo program maintains a global array of drifting floats, several thousand of them, each one sinking to about 2,000 meters, drifting for 10 days, then rising while measuring temperature and salinity and transmitting the profile by satellite. It is one of the great achievements of modern oceanography, and it works because floats are deployed from ships of opportunity. Where there are no ships, there are fewer floats, and the ones that drift in tend to be old. Coverage of the South Pacific Gyre has historically been thinner than coverage of the North Atlantic, which means that even our picture of the water there is assembled from fewer measurements than almost anywhere else in the open ocean. Hold all of that together and you have the first real shape of the problem. This is not a dangerous place because of what is in it. It is dangerous because of what has been subtracted from it. No food web, no fleets, no routes, no cables, no infrastructure, no observers, no assets. A hazard you can see is a problem you can plan around. An absence is not a hazard at all until the moment you need something, and then the absence is total. Which brings the story down from the map to the deck, because that is where the arithmetic actually lands. Picture a 50-foot boat there in a normal southern winter, and put one person on the foredeck in the dark, clipped on, working a sail change. The water under the hull is somewhere between 5 and 10 degrees Celsius. The wind has been in the west for 4 days. And here's the part people get wrong about the open ocean. The danger is not the wind speed you feel in that moment. It is the size of the ocean upwind of you. Wind builds waves by dragging on the surface, and the height and length of the resulting waves depend on three things: how hard the wind blows, how long it blows, and how far it blows across open water without hitting anything. That last one is called fetch. In an enclosed sea, fetch is bounded. Sail the English Channel, and the waves can only grow to the size the channel permits. In the Southern Ocean, the belt of water between roughly 40 and 60 degrees south, there is no land at all in a complete circle around the planet, except for the narrow interruption of the Andes and the Antarctic Peninsula. A westerly gale can push in the same direction for thousands of kilometers, with nothing to stop it. The result is not just big waves, it is long ones. Wave energy from a storm sorts itself out as it travels, with the longest waves moving fastest. So what arrives at a distant point is a smooth, ordered, enormous swell with 15 or 18 or 20 seconds between crests, generated by a low-pressure system that nobody aboard will ever see. It can be blowing 15 knots at your masthead, and you can still be lifted 8 meters by a wave born 2 days ago and 2,000 kilometers away. On a good day, that swell is majestic and almost gentle, a slow rise and fall like breathing. The trouble starts when a local gale puts a second, shorter, steeper wave train on top of the long one, running at a different angle. Two systems crossing produce occasional coincidences, moments when a crest from one lines up with a crest from the other, and the sea briefly builds something far larger and much steeper than the average. Steepness is what matters. A wave that is merely tall lifts a hull and puts it down. A wave that is tall and breaking drops several tons of moving water onto the side of a boat. And if that impact arrives on the beam, it can roll a vessel through 90 degrees before the crew has finished registering the noise. Everywhere else in the world, that is survivable in a specific way, because somewhere within reach, there is a lee. A lee is any piece of land that blocks the weather, and the entire history of seamanship is built on the assumption that one exists. You run for the shelter of an island. You duck behind a headland. You put a continent between yourself and the wind, and you wait. Sailors have been doing this for as long as there have been sails, and every pilot book and every routing chart in existence is organized around the idea that if conditions become intolerable, there is a direction in which they get better. At Point Nemo, there is no such direction. Whatever the sea is doing, it is doing it everywhere within 2,500 kilometers of you. And the only way to change your situation is to endure it until the system moves on. You cannot anchor because the water is roughly 4 kilometers deep, and that number deserves a caveat. The seafloor beneath Point Nemo has never been properly surveyed by ship. The depths shown on charts for that area come mostly from satellite altimetry, which infers the shape of the bottom from tiny variations in the height of the sea surface, caused by the gravitational pull of underwater terrain. It is a clever technique and it works at a resolution of kilometers, not meters. So the honest statement is that the water there is on the order of 4,000 meters deep, and that nobody has run a proper multi-beam line across it to check. 4,000 meters of water under the keel is not a hazard in itself. It becomes one the moment you want to stop, because there is no stopping. There is no bottom to hold you, no shore to hide behind, and no harbor within a week's steaming. Your endurance becomes the boundary of your world. How much fuel, how much food, how much water, how much structural margin the hull has left, and how long the people aboard can keep functioning without sleep. Now put a person in that water. This is where the numbers become brutally simple and where most people's intuition is wildly optimistic. Sea temperature around Point Nemo runs roughly between 5 and 10 degrees Celsius depending on season, and the human response to sudden immersion in water that cold happens in stages, each with its own clock. The first stage takes about a minute, and it is the one that kills fastest. Cold shock triggers an involuntary gasp, followed by hyperventilation that a person cannot voluntarily control. If the gasp happens underwater, which it frequently does when someone is thrown from a deck, water enters the lungs immediately. Heart rate and blood pressure spike. For anyone with an undiagnosed cardiac problem, that spike alone can be fatal. Survive the first 3 minutes, and you enter the second stage, which lasts perhaps 10 to 30 minutes, during which the muscles in your arms and hands cool to the point where they no longer produce useful force. This is called swim failure, and it arrives long before hypothermia. Your core is still near normal temperature. Your mind is clear. Your hands simply stop closing. Most people miss that detail entirely. A person in cold water does not slowly and gently fade. They lose the ability to grip a line or climb a ladder or hold a strop while their brain is still working perfectly well, which means they can watch a boat approach and be unable to do the one thing needed to be saved. Only after that does deep hypothermia set in over the following hours, as core temperature falls and consciousness goes. So the person overboard has, in round terms, a window measured in tens of minutes for a self-assisted recovery, and a few hours before the odds collapse entirely. Now measure the response against that window. The nearest search and rescue aircraft capable of covering that part of the ocean would be flying from Chile or New Zealand or Australia, and the transit alone exceeds the survival time by an order of magnitude. Even the long-range maritime patrol aircraft that navies operate, machines built precisely for reaching far offshore, have a practical radius of a couple of thousand kilometers and can only drop equipment. No aircraft can lift a person out of the middle of the South Pacific Gyre. There is no platform with the range, which means out there the entire rescue capability available to a human being in the water is the boat they just fell off, and the people still on it. On 26 March 2018, that arithmetic was tested in the most public way it has ever been tested in a race, on live tracking, with the whole sport watching. The Volvo Ocean Race Fleet was in the middle of its longest leg, from Auckland to Itajaí in Brazil. A run of some 7,000 nautical miles that crosses the South Pacific at high latitude and passes closer to Point Nemo than to any inhabited place. The race organizers had made a point of it. Their routing deliberately took the fleet through the region, and they had noted publicly what it meant. At times during that leg, the nearest human beings to the sailors were not on any ship or island but aboard the International Space Station, roughly 400 kilometers straight up, passing overhead at 8 kilometers a second. The boat in question was Sun Hung Kai Scallywag, a 65-foot one-design carbon racing yacht with 9 people aboard, running downwind in a big Southern Ocean sea. Their objective was not survival. It was a podium. They had won the previous leg into Auckland. They were sailing fast in conditions that suited them, and the pressure in that fleet was relentless, because every boat was identical, so the only variables were how hard the crew pushed and how much risk they accepted in sail choice and helming. John Fisher was 47, a British sailor, one of the most experienced people on the boat. He was on deck in heavy conditions when, according to the account the team gave afterwards, the boat performed an unplanned jibe. In a downwind jibe, they sank the mainsail and its boom crossed the stern from one side to the other, and a boom on a boat that size carries enormous energy. Fisher was struck and went over the side. He was wearing survival gear, and the account indicates he was likely unconscious when he entered the water. Everything that followed is a study in what the ocean removes. The crew immediately began a recovery, which in a southern ocean gale is not a simple maneuver. The boat had been traveling fast in the same direction as very large waves. To go back, they had to turn across those waves, slow down, reduce sail and wind strong enough to make every deck movement dangerous, and then try to hold a search pattern in a sea where the horizon disappears every few seconds behind a wall of water taller than the crew's eye level. Visibility from the deck of a yacht in a big swell is measured in the seconds when you are on top of a crest. In the troughs, you can see nothing at all. They searched for hours. The nearest other boat in the fleet was hundreds of miles away. There was no shore station, no aircraft, no vessel of opportunity, no amber ship to divert, because that quadrant of the Pacific has none. Race Control in Alicante was monitoring the situation by satellite from the other side of the planet, and the only asset in existence that could physically be brought to bear was the one boat that had already lost him. Late in the search, the team faced a second decision that is difficult to read even now. Conditions were deteriorating. The boat itself had suffered damage in the incident. The skipper, David Witt, made the call to abandon the search and head for shelter, and the nearest shelter was Chile, thousands of miles to the northeast. Witt described the decision publicly afterwards in blunt terms, saying that the safety of the remaining crew had become the priority and that he had to think about the 8 people still aboard. John Fisher was never found. Read that sequence again and notice what technology did and did not do. The boat had satellite communications good enough to report the accident to Europe within minutes. It had GPS accurate to a few meters, so the position of the man overboard was known precisely. It had an onboard tracking system that told Race Control exactly where every vessel in the fleet was, in real time. Every information problem was solved. Not one of those systems could put a hull alongside a person in the water, because there was no hull to put there. Knowing the exact coordinates of a place nobody can reach is not the same as reaching it. That is the shape the whole story keeps returning to, and it is the reason the emptiness at Point Nemo behaves so differently from other kinds of danger. In a busy sea, precision is a rescue tool. Tell someone exactly where you are, and someone comes. In an empty sea, precision is just an accurate description of your isolation. One more thing about that leg matters later. The Volvo fleet chose to be there. Nobody was forced through the South Pacific Gyre. They went because the Great Circle route from New Zealand to Brazil runs deep into the south, because the westerlies there are the fastest sailing wind on the planet, and because a competitive schedule made a longer, safer, more northerly track unacceptable. Racing rules eventually imposed an ice exclusion zone, a line beyond which boats may not sail, drawn to keep the fleet away from icebergs detected by satellite. Push the fleet north to avoid ice, and you compress them into a narrower band of ocean. Let them go south, and you gain speed and lose any possibility of help. Every safety decision out there is a trade of one exposure for another, and none of them creates safety in the ordinary sense. Which raises a question that the modern era tends to skip. If the emptiness is this hostile now, with satellites and carbon holes and weather routing, how did anybody deal with this ocean before any of it existed? The answer is that they did something smarter than going there. The Pacific was settled by the most accomplished ocean navigators in human history, and they did it without instruments of any kind. Polynesian voyagers crossed distances that European sailors would not attempt for centuries, in double-hulled canoes, carrying crops and livestock and families deliberately, upwind, into an ocean that covers a third of the planet. Rapa Nui, one of the 3 land masses that define Point Nemo's position, was reached and settled by people who arrived by sea. So was Ducey's neighbor Henderson Island and Pitcairn, and every scrap of habitable rock in that quarter of the world. Their method has been documented in detail, most famously through Mau Piailug, a master navigator from the island of Satawal in Micronesia, who in 1976 guided the voyaging canoe Hokulea from Hawaii to Tahiti with no compass, no sextant, no chart, and no clock. That voyage was organized precisely because scholars had argued the crossings must have been accidental drift. Piailug settled the argument by doing it, and later taught the method to Nainoa Thompson and a generation of Hawaiian navigators, which is why the technique survives today as a living practice rather than an ethnographic footnote. What the method actually consists of changes how you read the emptiness. A Pacific navigator holds a star compass in memory, the specific points on the horizon where particular stars rise and set, a mental circle divided by named stellar houses. At night, you steer by whichever star in the sequence is currently low on the horizon, changing to the next as each climbs too high to be useful. In daylight, you steer by the sun at its rising and setting, and by the direction of the swell in between. That swell reading is the sophisticated part. Long-period swell generated by distant persistent weather systems holds its direction for days and travels through and beneath local wind waves without changing course. A trained navigator learns to feel the primary swell through the motion of the hull and to distinguish it from a second and even a third swell train arriving at different angles, effectively using the ocean's own memory of far-off storms as a gyroscope. Navigators in the Marshall Islands built stick charts, lattices of palm ribs and shells, not as maps to be carried aboard, but as teaching tools for exactly this: how swell bends around an island, and how the interference pattern on the far side reveals land you cannot see. The mechanism underneath all of it is simple. Islands leave signatures in the water and air around them. Swell refracts around a landmass and produces a distinctive crossed pattern in its lee. Clouds pile up and hold still over a high island, sometimes with a green tint reflected from a lagoon. Certain birds, particularly the white tern and the noddy, fish out to sea by day and return to land at dusk, so their flight direction in the evening is a bearing to a coastline that may be 40 or 50 kilometers away. Drifting vegetation, changes in water color, the behavior of a particular species of dolphin near a reef entrance, all of it feeds into a system for expanding the effective target size of a small island from a few kilometers to something a canoe can reliably find. Hold that idea because it explains everything about why Point Nemo was never a destination. The Polynesian navigational system is not a system for crossing empty water. It is a system for detecting land. Every technique in it depends on islands acting as nodes, generating signals, refracting swell, holding clouds, sending birds out and drawing them back. A navigator on a long passage is continuously reading the ocean for these node signatures, and a voyage is a chain of them. Point Nemo is the one location on Earth where every node is out of range simultaneously. There is no refraction pattern in the swell, because the nearest coast is too far to bend anything. No land cloud because there is no land under the sky within a day's sailing in any direction. No land birds, because no bird that must return to a nest at night can operate that far offshore. The signal is not weak there. It is absent. That is a very different statement from saying the place is far away. It means that the most advanced natural navigation system humans ever developed had a specific blind spot, and Point Nemo sits at the exact center of it. There is no evidence anyone ever crossed it deliberately in the pre-instrument era. And there is no reason they would have. You would be sailing into a region where your entire method stops producing information, in a canoe with a limited water supply, to reach nothing. The Polynesian voyagers were not limited by courage or by boat quality. They were limited by information, and they responded intelligently. They went where the ocean spoke and stayed out of the one place where it says nothing. That is the difference between adapting to a region and forcing it to fit an external schedule, and it is a distinction that runs through every modern incident in this story. European ships changed the terms without changing the ocean. Once the chronometer solved longitude in the late 18th century, a navigator could fix a position anywhere, including in water that offered no clues at all, latitude from the sun, longitude from time, and suddenly a ship's position no longer depended on the ocean cooperating. That capability is what allowed sailing routes to be drawn straight across regions that Polynesian voyaging had rationally avoided. Then came a genuine transformation. Satellite navigation put a position accurate to a few meters on every bridge and every cockpit on Earth, continuously, in any weather, with no skill required. Weather satellites made it possible to watch a southern ocean depression form and track it for days before it arrived. Satellite communication made it possible to speak from the middle of the Pacific to a rescue center on another continent. Distress beacons, working through the International COSPAS-SARSAT system, meant that a single switch could report an emergency and its position to a network of satellites that relays it to a coordination center within minutes. Every one of those was a real advance. All of them together solved the problem of knowing. None of them touched the problem of distance. That gap is the engine of everything that follows, and the first entity to fully exploit it was not a shipping company or a research institute. It was a space program, which noticed something that no sailor could use and that no rescue service could match. If there is a piece of the Earth's surface where nothing and nobody ever goes, then it is the safest place on the planet to drop something enormous out of the sky. On 23 March 2001, the Russian space station Mir came down there, and the operation is worth going through carefully because it is the cleanest demonstration in existence of what we can and cannot do at Point Nemo. Mir had been in orbit since February 1986. Over 15 years it grew from a single core module into a complex of 7 pressurized modules, with a total mass of about 143 tons, the largest artificial object then in orbit, apart from the young International Space Station. It had hosted 104 people from a dozen countries. It had survived a fire, a collision with a Progress supply freighter in 1997 that punctured the Spectre module and cost the station a quarter of its power, repeated computer failures, and a period in the late 90s when Russian funding collapsed to the point where flying the station at all was in question. By 2000, the structure was aging badly and the money was gone. The Russian government decided to dispose of it, over public objections and a late private effort to keep it flying as a commercial platform. The decision was made on hard grounds. Mir was in a decaying orbit and losing altitude continuously to atmospheric drag, and the moment it dropped below the altitude at which its engines could still control the descent, the choice of where it landed would pass from Russian mission control to physics. That was the pressure. Not a schedule, not a budget cycle. An object as heavy as a loaded railway carriage was going to reach the ground somewhere, and the only question was whether human beings picked the somewhere. They had reason to care, because the history of large, uncontrolled re-entries was already embarrassing. In July 1979, NASA's Skylab, about 77 tons, came down without a controlled deorbit capability after solar activity increased atmospheric drag and pulled it in earlier than predicted. Controllers managed to tumble it to shift the footprint, hoping to drop the debris into the Indian Ocean. Large pieces landed in Western Australia, scattered across the region around Esperance, and the local council famously issued the United States a small fine for littering. Nobody was hurt. It was luck. In February 1991, the Soviet station Salyut 7, docked with the Cosmos 1686 module and massing around 40 tons, came down uncontrolled after its own orbit decayed faster than expected. Debris fell over Argentina, near the town of Capitan Bermudez. Again, nobody was hurt. Again, it was luck. Twice in 12 years, the world had rolled the dice with tens of tons of metal and won. Mir was nearly twice the mass of Skylab and more than 3 times that of Salyut 7. The Russians had no intention of rolling it a third time. The instrument they used to control the descent was a supply ship. On 27 January 2001, an uncrewed Progress M15 freighter launched from Baikonur and docked with the station. It was a standard cargo vehicle modified for the job, carrying no cargo at all in the usual sense, just propellant, roughly 2.5 tons of it, considerably more than a normal resupply flight. The Progress became, in effect, a strap-on engine for a 143-ton structure that had none of its own worth using. There was one condition that had to hold, and it was not guaranteed. The station's orientation and its systems had to remain stable enough for the burns to be executed in the right direction. Mir had a history of losing attitude control and tumbling, and a tumbling station cannot be aimed. In late 2000, the station's power and computers were revived specifically so it could be flown for its own destruction, and controllers at the Mission Control Center in Korolyov spent weeks nursing it into a stable configuration and lowering the orbit gradually through atmospheric drag. By March, Mir was in an orbit of roughly 220 kilometers and dropping. Then came the sequence. The first burn, in the early hours of 23rd March, lowered the low point of the orbit. The second, one orbit later, lowered it further. Then, a gap, deliberately, to allow tracking and confirmation. And finally, the third and longest burn, more than 20 minutes of thrust, which dropped the station's perigee to the point where the atmosphere would take it. There was no second attempt available. Once the propellant was spent, whatever trajectory Mir was on was the trajectory it would fly. If the third burn had failed halfway, the station would still have come down within days, at an unpredictable point along a ground track that crosses inhabited land on most orbits. The burn worked. Mir entered the atmosphere over the South Pacific at around 6 in the morning UTC and began to break apart at an altitude near 100 kilometers as aerodynamic forces exceeded what a structure built for the vacuum could withstand. Solar arrays tore away first. The pressurized modules, thin aluminum cylinders never designed to fly through air at Mach 20, ruptured and burned. Estimates at the time suggested somewhere between 1,000 and 1,500 individual fragments survived to hit the water, with a total surviving mass in the range of 20 tons. The critical number is the length of the resulting footprint. Different fragments have different masses and different drag characteristics, so they decelerate at different rates and fall along the trajectory rather than at a single point. Denser objects, such as docking assemblies and gyrodynes and pressure vessels, fly farther. Light structures slow rapidly and drop short. The predicted debris corridor for Mir was on the order of 1,500 kilometers long and about 100 wide, which is why the entire operation depended on having an area of ocean that big with nothing in it. Russian authorities declared a closure zone, notified mariners and aviation agencies, and air traffic was rerouted. In Fiji, where the re-entry track passed within visual range, chartered aircraft went up carrying observers and camera crews, and people on the ground in Nadi watched a line of white and orange fragments cross the pre-dawn sky, trailing smoke, breaking into smaller pieces as they went, several minutes from horizon to horizon. Taco Bell, the American fast food chain, had towed a large floating target into the Pacific and announced that if a piece of Mir struck it, every person in the United States would get a free taco. Nothing hit it. The stunt is a footnote, but it captures something real about the confidence surrounding the operation. The company was betting against a specific outcome in a specific patch of ocean, and the mathematics of re-entry made that bet extremely safe. Consider what had just been demonstrated. 143 tons of decaying hardware, flying at nearly 8 kilometers per second, was steered out of a decaying orbit barely 200 kilometers up onto a piece of ocean where nobody lives, using an engine that had been launched 2 months earlier and docked to the front of it, with a resulting impact area comfortably inside the intended zone. The delivery accuracy for the center of that footprint was on the order of a few kilometers of the aim point. And here is the reversal that ought to sit uncomfortably. There is no vessel, no aircraft, no organization, no Navy on Earth that could put a doctor onto a boat at that same location within a week. We can hit Point Nemo. We cannot go to it. The one thing humanity does reliably at the most remote place in the world is aim garbage at it. That is not a rhetorical flourish. It is an operational fact with a name. The region is designated in navigational and space agency documents as the South Pacific Ocean Uninhabited Area, a defined stretch of water used as the disposal target for spacecraft that need to be destroyed on the way down. Mir was the largest object ever aimed at it, but it was neither the first nor the last, and it is far from alone down there. The practice began quietly. The Soviet Union started deorbiting spacecraft into the South Pacific in the early 1970s, and the Salyut stations that preceded Mir ended their lives in the same general region. Since then, the traffic has been continuous. Estimates compiled from public records put the number of vehicles disposed of in that area at more than 250, and by some counts, well over 300. The bulk of them are Russian Progress freighters, the same vehicle type that pushed Mir down. Each one flies cargo up to a station, spends months attached as a rubbish bin for waste and used equipment, and is then undocked and deliberately burned in over the South Pacific. There have been well over 100 of those. Japan's H-2 transfer vehicles, the Kunitori series, 9 of them, each about 10 tons empty and 16 tons loaded, followed the same path between 2009 and 2020. Europe's automated transfer vehicles did too, 5 of them, the largest resupply craft ever flown to the International Space Station at around 20 tons each. Europe's first vehicle is the interesting one. Jules Verne launched in March 2008, docked automatically with the space station using laser guidance to align itself with the target on the Russian segment, and remained attached for 5 months. On 29 September 2008, it was undocked and deorbited over the South Pacific, and the European Space Agency and NASA did something unusual with the destruction. They instrumented it. 2 aircraft flew a coordinated observation mission from Tahiti, carrying spectrographic and imaging equipment, tracking the breakup from above, to gather data on how a large structure comes apart during re-entry. Engineers wanted that data because the models used to predict which components survive were, and largely remain, uncertain. That is a small detail that says something large. To understand how our own hardware breaks up, we had to charter aircraft and fly them out over the empty Pacific to watch it happen from the air. Because there is no other way to observe an event that occurs 80 kilometers above the loneliest water on Earth. So there is now, on the seabed under and around Point Nemo, a field of surviving debris built up over half a century. Fuel tanks, docking mechanisms, structural frames, reaction wheels, titanium pressure vessels, pieces of at least 6 space stations and hundreds of cargo ships. It lies 4 kilometers down, scattered across a zone thousands of kilometers long, in water so poor in nutrients that biological colonization is likely to be extraordinarily slow. Nobody has ever seen it. Not a photograph, not a sonar mosaic, not a single confirmed recovered fragment. There has never been a survey of the impact area. That is not because the technology is missing. We have located wrecks in deeper water. The reason is the one that governs everything else here. A survey would need a vessel with deep-water sonar and a remotely operated vehicle, steaming roughly 2 weeks each way from the nearest capable port. It would have to hold station in southern ocean swell for as long as the work took, and it would be searching a debris field the size of a small country for objects a few meters across with no commercial return and no scientific urgency behind it. Nobody is buying that ship time. Everything about that field is inference. We know approximately what went in, because re-entry disposal is documented. We know approximately where it went, because the trajectories were planned. What is actually resting on that abyssal plain, in what condition, spread over what area, is a question that has been open since 1971 and has never once been examined directly. Which raises the next question, and it is the one that starts to expose the real hierarchy of difficulty here. If we cannot get down to look at our own wreckage, what have we actually managed to learn about that ocean at all? The answer is a small, strange, and much harder-won body of knowledge than most people would guess. And it came from a drill ship on a schedule set years in advance. The ship was the JOIDES Resolution, a converted oil exploration vessel about 140 meters long, with a drilling derrick rising 60 meters above the waterline, operated for the Integrated Ocean Drilling Program. She has no anchors that matter at these depths. Instead, she holds position over a target on the seafloor using computer-controlled thrusters fed by acoustic beacons dropped on the bottom, adjusting continuously against wind, current, and swell, so that a drill string 4 kilometers long stays in a hole a few tens of centimeters wide. In October 2010, she sailed from Papeete in Tahiti for Expedition 300 Sander 29, bound for the South Pacific Gyre. The co-chief scientists were Stephen DeHont of the University of Rhode Island and Fumio Inagaki of Japan's Marine Science Agency, and the scientific party was drawn from a dozen countries. The plan was to core the sediment at 7 sites along a transect that ran from the edge of the gyre through its center and on toward the Antarctic, and finish at Auckland in December. The reason it took that form matters because it demonstrates the constraint better than any statistic. This was not a decision made by a scientist who wanted to look at Point Nemo. Ship time on a drilling vessel like that costs on the order of $100,000 a day, and the schedule is set by an international proposal system with review cycles measured in years. A proposal is written, evaluated, ranked, deferred, revised, and eventually slotted into a global track that moves the ship around the world in a sequence designed to minimize transit. Expedition 300 existed because a scientific case had been argued and won long before, and because the vessel's routing happened to allow a South Pacific transect that season. You cannot go to the middle of the South Pacific Gyre because something interesting happened last week. There is no rapid response. The barrier is not that we lack the knowledge or the equipment. The barrier is logistics, and logistics operate on the timescale of years. What they found justified the wait, and it began with the sediment itself. On most of the ocean floor, sediment accumulates from a rain of dead plankton, mineral shells, dust, and clay, building up steadily over geological time. Rates vary widely, but in productive regions you can see several centimeters per 1,000 years, and in some coastal settings far more. Out in the South Pacific Gyre, Expedition 329 found sediment accumulating on the order of a meter per million years, and in places less. A single millimeter of that mud can represent 1,000 years of falling material. Think about what that means physically. Put your finger on the seafloor there and you are touching a layer that took a human lifetime to form. The total sediment blanket over the basalt basement at several of those sites was only tens of meters thick, on crust that is tens of millions of years old, because so little has ever fallen through that water. The second finding was the one that overturned an assumption. In ordinary marine sediment, oxygen disappears within centimeters of the seafloor. Bacteria in the top layer consume organic material and use up the available oxygen almost immediately, and everything below is anoxic. That pattern is so consistent that it is taught as a basic feature of how the seabed works. At the South Pacific Gyre sites, the drilling team measured oxygen present through the entire sediment column, all the way down through tens of meters of mud to the volcanic rock beneath. Oxygen was penetrating the full thickness of the sediment and into the basement rock itself. The explanation is a direct consequence of the emptiness above. Oxygen persists at depth only if nothing consumes it, and nothing consumes it because so little organic material ever arrives. The water column is so poor in life that the rain of dead matter reaching the bottom is too thin to sustain the microbial respiration that normally strips the oxygen out. What Expedition 329 documented was not a quirk of one core. It was the sedimentary signature of the least productive ocean on the planet, written continuously into the seabed over tens of millions of years, and there was life in it. Microbial cells were present in those sediments, but at abundances several orders of magnitude below what is found in ordinary marine sediment, in some samples close to the detection limit of the methods used. Those communities appear to survive on energy budgets so small that individual cells may divide on timescales of centuries or longer, subsisting in part on hydrogen produced by the radioactive decay of elements in the surrounding minerals, splitting water molecules. Life there is not thriving, and it is not dying. It is idling, at a rate that makes the word metabolism feel like an exaggeration. That result reframes the whole region. The emptiness is not a surface phenomenon. It goes to the bottom, into the rock, and back tens of millions of years. Point Nemo is not a blank spot on a map of an otherwise busy ocean. It is the center of the largest and most persistent biological desert on the planet, and the desert is vertical as well as horizontal. Notice also what the expedition could not do. The Joid's Resolution passed through that region, drilled her holes, and left. There was no follow-up cruise the next season to check an anomaly. The samples went into repositories and were analyzed for years afterwards, because getting more was not an option anyone could exercise on demand. Even at the level of a well-funded international drilling program, the South Pacific Gyre gets visited when the ship happens to be crossing it and not otherwise. So the sediment was explained. The water was not, and that gap took another ship and another 5 years to start closing. In December 2015, the German research vessel Sonne left Antofagasta in Chile on a cruise designated SO245, given the working name UltraPac, and led by Bernhard Fuchs of the Max Planck Institute for Marine Microbiology in Bremen. The Sonne was almost new, a purpose-built research ship commissioned in 2014, 116 meters long, designed for long endurance in remote water. Her track ran west and south across the heart of the South Pacific Gyre, passing near the region of Point Nemo, and ended in Wellington in January 2016. Their objective was the microbial life in the water column itself. How many cells, what kinds, how they are distributed with depth, and how they survive in water that receives almost no nutrients. It sounds like a narrow question. The answer was one of the more striking measurements made in modern biological oceanography. Cell counts in the surface waters of the gyre came in at roughly a third of the values typical for other ocean gyres, among the lowest ever recorded in the open ocean. Not a third lower, a third of the total. In a body of water already understood to be poor, this was the poorest patch, and the measurements confirmed it in a way that satellite estimates of surface color never could. Here is where the physical consequence becomes visible and slightly eerie. The reason ocean water looks blue-green rather than pure blue is largely the presence of living cells and the dissolved organic material they produce, which absorb and scatter light in particular parts of the spectrum. Strip out the biology, and you are left with water whose optical properties approach those of pure water in a laboratory. In 2004, a French expedition aboard the research vessel L'Atalante, the Biosoap cruise, crossed the gyre between the Marquesas and the Chilean coast, measuring exactly that, and reported the clearest natural seawater ever documented with sunlight, including ultraviolet, penetrating to depths well beyond what is normal in the open ocean, which produces one of the reversals that makes this place difficult to think about clearly. The water at the center of the South Pacific Gyre is the clearest natural water on Earth, and it is clear for the same reason a desert sky is clear. There is nothing in it. The most beautiful water in the world is a measurement of absence, and the ultraviolet light driving deep into it is itself part of the reason so little survives near the surface. That clarity has a practical edge that matters to anyone who ends up in that water. Deep light penetration and warm, strongly stratified surface layers reinforce the barrier that keeps nutrients trapped below, which keeps productivity low, which keeps fishing fleets away, which keeps ships away, which is the reason nobody is coming. The optics and the rescue problem are the same fact seen from two directions. By the middle of the last decade, then, the picture from the region was coherent, and it was built on an absurdly small number of visits. A drill ship passing through in 2010, a German research vessel across the southern summer of 2015 and 2016, a French cruise in 2004, a handful of others. Add up every scientific ship day ever spent in the neighborhood of Point Nemo, and it would not fill a season of work in the North Sea. If you cannot get ships there, and you cannot get aircraft there, there is one thing you can still do at almost unlimited range, because the ocean carries it for you. You can listen. Sound behaves in seawater in a way that has no equivalent in air. Around a kilometer below the surface, in most of the world's oceans, there is a layer where the speed of sound reaches a minimum, because pressure increases with depth, while temperature decreases, and the two effects cancel at a particular level. Sound entering that layer gets bent back into it from above and below, and instead of spreading in all directions, it becomes trapped, propagating horizontally for enormous distances with very little loss. It is called the deep sound channel, and a low-frequency signal injected into it can be detected thousands of kilometers away. The United States Navy built its Cold War submarine surveillance system on this, laying arrays of hydrophones on the seabed and cabling them ashore. When parts of that capability opened up to civilian science, the National Oceanic and Atmospheric Administration's Pacific Marine Environmental Laboratory began using hydrophone networks to study underwater sound, including an autonomous array deployed across the equatorial Pacific. In the summer of 1997, that system recorded something that has caused more confusion about Point Nemo than any other single event. The sound was picked up several times. It rose in frequency over about a minute. It was extremely loud, and it was detected on sensors more than 5,000 kilometers apart, which is what made it remarkable. Anything audible at that separation has to be releasing a very large amount of acoustic energy. Because of the rising pitch, the recording was nicknamed the bloop. Locating a sound in the deep sound channel involves comparing arrival times at multiple widely separated sensors, and the resulting position is not a pinpoint. It is a region. For the bloop, that region was in the broad South Pacific, somewhere off the coast of southern Chile, west of the tip of South America. The published rough position, in the neighborhood of 50 degrees south and 100 degrees west, is well over 1,000 kilometers from Point Nemo, which by any reasonable standard means the sound was not detected at Point Nemo at all. The phrase that stuck anyway was that the bloop came from near Point Nemo. It is journalistic shorthand, and it has been repeated so often that it now travels as fact. Two remote things in the same very large quadrant of the Pacific got merged, largely because Point Nemo is the only name most people know for that part of the world. It is a small distortion with an outsized effect, because it attached the emptiest place on Earth to a genuine acoustic mystery. The mystery itself was real for a while. The profile of the sound, particularly its rise in frequency, had a rough resemblance to the calls of large marine animals, and the acoustic energy involved was far greater than any known animal produces. That combination is what generated the speculation, most of it far beyond anything the data supported, and the story spread through a decade of documentaries and internet folklore as evidence of something enormous and undiscovered in the deep South Pacific. Resolution came from more listening in a different place. NOAA researchers, including Robert Giac, deployed hydrophones in the Southern Ocean around the Antarctic and the Scotia Sea in the following years, in part to study ice. What they recorded there was an enormous volume of noise generated by ice, icebergs grounding on the seabed and scraping across it, large tabular bergs fracturing, ice cracking under stress. These events produce exactly the acoustic signature that had puzzled everyone, including the loudness and the characteristic rise in frequency, and they occur constantly around Antarctica. NOAA's conclusion was that the bloop was an ice quake, most likely a large iceberg cracking or calving somewhere in the Antarctic region. Its sound carried thousands of kilometers through the deep sound channel to hydrophones in the tropical Pacific. Sit with the shape of that for a second, because it is the second major reversal in this story, and it is not really about a sound at all. Remote sensing gave us the ability to detect an event in a part of the ocean nobody could visit. It gave us a loud, real, physically significant signal. What it could not give us was context. And into that gap, the human imagination poured a decade of monsters. The technology that reached the unreachable place also manufactured a mystery, and it took years of additional fieldwork in an entirely different ocean to take it apart. There is a harder version of the same lesson. Hydrophones can hear an iceberg breaking 5,000 kilometers away. They cannot hear a person in the water 500 meters from a hull, and they cannot pull anyone out. Remote sensing extends perception, not reach. And at Point Nemo, the distance between those two things is larger than anywhere else on the planet. Which brings the story back to the surface, and to the woman in the upside-down boat. In September 1998, the Around Alone race started from Charleston, South Carolina, a solo circumnavigation in stages, one of the hardest events in sport. Isabelle Audissier was one of the favorites and one of the most respected sailors in the fleet. She was French, an engineer by training, and a former fisheries scientist, and she had already done what almost nobody in the sport had done, winning a leg of the previous edition of the race by an enormous margin. She also knew, in the most personal way possible, what the Southern Ocean does to boats. In the 1994 to 1995 running of the same race, she had been dismasted and then rolled in the Southern Indian Ocean, losing her boat's coach roof, and had been rescued by the Royal Australian Navy after a long-range aircraft located her. Her objective in February 1999 was straightforward: sail the fourth leg from Auckland in New Zealand to Punta del Este in Uruguay, across the South Pacific and around Cape Horn, and stay in contention. Her boat, PRB, was a 60-foot ocean racer, purpose-built for exactly this water. She was ahead of much of the fleet and sailing in conditions that were severe, but not exceptional for that latitude. The initial condition here is genuine competence. This was not an amateur adventure. She was a professional in a proven boat on a route she had sailed before, with all the equipment the era offered: satellite communications, weather files, distress beacons, watertight compartments. Deep in the South Pacific, days of sailing from any coast in the empty quadrant between New Zealand and Cape Horn, the boat was rolled in a heavy sea and did not come back up. That last part is the mechanism that matters, and it deserves explanation, because most people assume a capsized sailing yacht rights itself. Usually, it does. A monohull with a heavy keel and a deep bulb of lead is designed so that when it heels past a certain angle, the weight of the keel generates a righting force that rotates the boat back upright. The angle beyond which that stops working is called the limit of positive stability, and past it, the boat is stable upside down, held there by the buoyancy of the hull. For a racing yacht with a wide, flat, powerful hull shape, the inverted position can be very stable indeed. A wide beam is fast downwind, and it also makes an excellent platform for floating keel up. To recover, an inverted monohull generally needs the sea to roll it through the rest of the circle, or needs its rig to still be attached and acting as a brake. In Audissier's case, the boat stayed inverted. Her mast had gone. Her cabin was now a low, dark, cold air pocket beneath the waterline, with everything that had been stowed on shelves now on what used to be the ceiling. She activated her distress beacon. Here is where the geography does its work, and where every part of the earlier arithmetic comes due at once. The signal was picked up by satellite and relayed, and the race organization and the maritime authorities in New Zealand knew, within a short time, exactly where she was. Precision was not the problem. The problem was the list of assets that could act on that precision. And in that part of the ocean, the list was almost empty. There was no aircraft with the endurance to reach her position, loiter, and be useful. There was no naval vessel within a reasonable steaming time. There were no merchant ships crossing that water, for all the reasons the gyre and the great circles guarantee. What existed was the race fleet, and the nearest boat in it was Giovanni Soldini, an Italian sailor, aboard Fila, who was in the same leg of the same race and had his own result to protect. Soldini was given her position and turned toward it. Understand what that decision cost him and what it required. He was racing. He had been sailing hard for weeks and was in a position to win. Diverting meant sailing away from his optimum route, upwind, or across the sea state depending on the geometry, into worsening conditions alone, with no possibility of help for himself if he was damaged in the process. It also meant sailing toward a target that was moving. An overturned hull does not stay put. It drifts with the current and is pushed by the wind, and the beacon position he had been given was a snapshot of where she had been, not where she was. Search in that environment is a physical problem, not a navigational one. A hull floating keel up sits almost awash, and Soldini was alone, which meant that every minute he spent trimming, steering, or checking a position was a minute with nobody watching the water. Add the drift to that. The area she could be in expands in every direction, while the searcher closes on where she was. It is entirely possible to sail within half a mile of an object like that and never see it. Soldini reached the area after roughly a day of sailing and found the boat. Accounts of the recovery describe him coming alongside the upturned hull and hammering on it to make contact, unable to know whether she was alive inside, unable to see in. She answered. She had been in that inverted compartment in the dark for around 24 hours, in a boat full of freezing water, with the air pockets shrinking or holding depending on the motion. She got out through a hatch in the hull, and he took her aboard. Then he went back to racing. Soldini resumed the leg and went on to win the event. The thing to extract from this incident is not heroism, although there was plenty of it. It is the structure of what happened. Every piece of technology performed. The beacon worked, the satellites worked, the coordination worked, the position was accurate, and the entire rescue capability that existed in that part of the world consisted of one competitor in the same sporting event who happened to be within a day's sail and chose to give up his race. There is a version of this story in which nobody else is racing that week, and in that version, Isabelle Autissier dies inside a floating hull whose exact coordinates are known to authorities on 3 continents. That is not speculation. It is the direct implication of the Amber Hole, the absent shipping lanes, and the aircraft range limits. The Southern Ocean had already made that lesson explicit 2 years earlier, in a different sector, in a way that showed the other side of the problem. What happens when a state does have an asset, and what that asset has to go through. In the 1996 to 1997 Vendée Globe, another solo round-the-world race, a series of boats came apart in the southern Indian Ocean south of Australia. On Christmas Day 1996, the French sailor Raphael Danelli's boat was rolled and swamped, and he ended up standing on a partly submerged deck in a survival suit. The nearest human being was the British sailor Pete Goss, roughly 160 miles downwind. Downwind is the operative word. To reach him, Goss had to turn his boat around and sail back into a storm with winds reported in the region of 60 knots. And it took him around 2 days to cover that distance. He was knocked flat during the attempt. An Australian Air Force aircraft found Danelli first and dropped him a life raft, which is the only reason he was still alive when Goss arrived to take him off. 10 days later, in the same stretch of ocean, 2 more boats went over. Thierry Dubois was capsized and ended up on the upturned hull of his yacht, and Tony Bullamore's boat lost its keel, inverted, and stayed that way with him trapped inside. The Australian response is the clearest illustration in modern maritime history of what a real long-distance rescue actually involves. And it is worth walking through in order, because the popular version compresses days into a moment. First, recognition. Both men had emergency beacons, and the signals reached the Rescue Coordination Center in Australia. The center knew that two sailors were in trouble, roughly 2,000 kilometers southwest of Perth. What it did not know was their condition, whether they were inside their boats or whether they were alive. Second, authorization and preparation. A rescue at that range is a military operation, not a Coast Guard one. The Royal Australian Navy detached the frigate HMAS Adelaide from other duties and sent her south. A warship of that class can make good speed, but 2,000 kilometers is 2,000 kilometers, and steaming it takes days, during which the men in the water are on their own clock. Third, air search. Royal Australian Air Force P-3 Orion Maritime Patrol aircraft flew out from Western Australia, which meant hours of transit each way for a limited period on station. Those aircraft found Dubois, who was on top of his hull and visible, and dropped him a life raft. They could do nothing else for him. There is no way to lift a man from that far offshore by air. Dropping the raft was the whole of the available intervention, and it kept him alive until the ship arrived. Bullimore was a different problem entirely, because there was nothing to see. His yacht was floating upside down, and he was inside it, in an air pocket, in water cold enough that he later described losing feeling in his hands, rationing a small amount of drinking water and chocolate, hearing aircraft pass overhead, and having no way to signal them. From the air, an inverted hull looks like an abandoned wreck. There was no evidence he was alive, and there were 4 days between the capsize and the arrival of the ship. Fourth, approach and transfer. The Adelaide reached Dubois and recovered him first, then went to the inverted hull. Sailors from the ship approached in a small boat and struck the hull, the same crude technique that would be used 2 years later in the Pacific, because there is no better one. Bullimore heard it, and he swam out from under the hull and surfaced beside them. The whole operation took days, involved a frigate and long-range aircraft and a substantial slice of a national defense force, and it cost the Australian taxpayer a sum that was debated publicly for months afterwards. Now apply that template to Point Nemo, and the comparison is where the shock lives. Everything the Australians did was possible because the casualties were roughly 2,000 kilometers from a major air base and a naval port with a frigate alongside. That is a long way. It is also, by the standards of Point Nemo, close. From the position of Point Nemo, the nearest place with a runway capable of handling a long-range patrol aircraft and any meaningful search and rescue infrastructure is thousands of kilometers away, and the nearest naval base with a suitable vessel further still. There is no equivalent of Perth. Chile is roughly 3,500 kilometers to the east, and New Zealand around 5,000 to the west. And the intervening water is exactly the water with no ships in it. A warship making 20 knots covers around 900 kilometers a day in flat water. In Southern Ocean swell, she will not make 20 knots, and she will burn fuel at a rate that raises the question of whether she can get back. Do the arithmetic honestly, and a naval response to a casualty at Point Nemo is a passage of 4 to 6 days at best, from the moment a government decides to commit a ship, assuming a suitable ship happens to be free, fueled, and pointing the right way. Nobody in the water survives 4 days. Nobody inside a flooded, inverted hull survives it either in most cases. On paper, the region is covered. The world's oceans are divided into search and rescue regions assigned to individual states by international agreement, and every square meter of the South Pacific falls inside one of them. New Zealand's region alone runs to something in the order of 30 million square kilometers, an area vastly larger than the country itself, one of the largest such responsibilities in the world. The coordination centers are real, professional, and permanently staffed. What they do not have and cannot have is anything parked near Point Nemo. Coverage on a chart is not coverage, in fact. A rescue region is a promise to coordinate, not a promise to arrive, which is precisely the gap that the next 2 decades of technology were supposed to close. And this is where the illusion of control becomes measurable, because we can compare the same accident in 2 different eras and see exactly what improved. On 21st September 2018, an Indian naval officer named Abhilash Tomi was lying on the floor of his cabin in the southern Indian Ocean, unable to move, roughly 1,900 nautical miles from the nearest land, typing short text messages on a satellite tracker. He was competing in the Golden Globe race, an event with an unusual and deliberately hostile premise. It was staged to mark 50 years since the original 1968 solo nonstop round-the-world race, and the rules required competitors to sail boats of a similar type and vintage, and to use only the technology available then. No GPS for navigation, no modern chart plotters, sextant, paper charts, wind vane self-steering, and long-wave radio. The entrants carried safety equipment that the organizers controlled and sealed, including satellite trackers and beacons. But using them for navigation meant retirement. Tomi was not a novice at any of this. He was a serving officer in the Indian Navy, a naval aviator, and in 2012 and 2013 he had sailed solo, nonstop, and unassisted around the world, the first Indian to do it. His boat, Thuria, was a replica of a design from the 1960s, built for the race in India. His objective was to finish. His condition of apparent control was a proven sailor in a boat built to a proven design, in a race he had spent years preparing for. The first warning was in the weather. A deep, low-pressure system was crossing his part of the Indian Ocean, and the fleet knew it was coming, because although they could not navigate by satellite, they could receive weather information by radio. Wind was reported at around 70 knots, with a sea state to match, and the boats in that part of the fleet were doing what sailors do in those conditions, reducing sail to almost nothing, securing everything below, steering to keep the stern to the worst of the sea, and waiting. Storm tactics in a small boat are a set of imperfect choices. Run before the sea and you risk being pitch-poled, thrown end over end when the bow buries in the back of the wave ahead. Lie to a sea anchor or a drogue and you slow down but accept enormous loads on the boat and on the gear. Turn beam on and you invite a breaking crest to roll you. Every option removes a different risk and adds another, and the correct answer depends on the boat, the wave period, and how tired the person at the helm is after several days without proper sleep. Thuria was rolled and dismasted. The rig came down, the boat came back upright without her mast, and Tomi was thrown across the cabin. The injury was to his spine, in the lower back, and it left him unable to stand or move meaningfully. He was alone, on a boat with no mast, in a survival-scale storm, in one of the emptiest sectors of the Southern Ocean. Here is where the modern era shows what it genuinely changed. He had a tracker capable of sending short text messages. He used it, and the messages that came out of that cabin were spare and functional, reporting that he was severely injured, that he could not move, that he needed a stretcher. His exact position was known continuously. His condition was known. The race organizers in France and the rescue authorities in Australia, who held responsibility for coordinating in that part of the ocean, were working with better information than any rescue coordinator in 1997 could have dreamed of. None of that shortened the distance by a single mile. The response that followed is the most instructive sequence in this entire story, because it involved multiple nations. It was executed competently, and it still took days. Australia's Rescue Coordination Center took charge of the coordination. India's Navy began moving. France became central for the practical reason that the nearest usable land was French, the tiny sub-Antarctic Amsterdam Island, in the far southern Indian Ocean, a French research station roughly 2 days sailing from Tomi's position, with a patrol vessel that supported it. The first asset to reach him was not a rescuer at all. It was another competitor. Gregor McGuckin, an Irish sailor, had been dismasted in the same storm and was in his own emergency, and he began motoring and jury-rigging his way toward Tomi while damaged himself. That is the Autissier pattern repeating 20 years later, with the same underlying cause. In that ocean, the only vessels nearby are the other people foolish or brave enough to be out there. An Australian aircraft made the long transit to overfly the position and confirmed that Thuria was still afloat and that Tomi was responding. A French fisheries patrol vessel, the Osiris, was dispatched from the Amsterdam Island area and steamed toward the position. The Australian Navy diverted the frigate HMS Ballarat. Indian naval ships were also directed to the area. The Osiris got there first, roughly 3 days after the dismasting. 3 days. A man with a spinal injury, immobile, in a boat with no rig, taking whatever motion the sea gave him for 3 days, while the most capable maritime nations in the region moved everything they had. The transfer itself required care. He could not climb, could not assist, could not be handled roughly with a back injury of unknown severity. The Osiris crew took him off Thuria on a stretcher, then carried him to Amsterdam Island, from where he was eventually transferred onward by an Indian naval ship for proper medical treatment. He survived, had surgery on his back, and, in one of the more remarkable footnotes in the sport, returned to the same race 4 years later and finished second. Now compare the two eras directly because the comparison is the point. In 1997, Tony Bullimore was inside an inverted hull for 4 days with no way to tell anyone he was alive. In 2018, Abhilash Tomi was texting his condition in real time from a position known to the meter. The information problem was solved completely in the intervening 21 years. The delay barely moved. 4 days then, 3 days now, and the difference is mostly luck about where the nearest ship happened to be. This is the illusion in its clearest form. Communication technology improved by orders of magnitude. Distance did not move at all. A satellite phone cannot make water shorter. And there is a second-order effect that deserves saying plainly. Because communication improved, people push further. Better forecasting extends operating windows. Better beacons make dangerous events feel recoverable. Races run in remoter water. Expeditions plan longer routes. And the accepted risk boundary quietly moves outward. Because everyone involved knows help can be called. The calling is not the hard part. It never was. Point Nemo is where that logic reaches its terminal state. Toudoual, because it is the one place where even the modest options available to Tomi do not exist. There is no Amsterdam Island. There is no French patrol vessel 2 days away supporting a research station, because there is no research station and nothing to support. Subtract the island and the ship, keep everything else about that accident, and Abhilash Tomi is a man with a broken back sending accurate text messages into a system that has nothing to send back. That specific scenario has been tested by people trying to go there on purpose, and it stopped an expedition dead. Chris Brown is a British businessman and adventurer who has made a project of visiting poles of inaccessibility, the calculated points farthest from any coast on each continent and in each ocean. Point Nemo is the oceanic one and the hardest, not because anything there is technically difficult, but because of the logistics that this whole story has been describing. Chartering a vessel with the endurance and the range to cross that water, provisioning it for weeks, and accepting that from the moment you leave port, you are outside the reach of any emergency service. According to press accounts at the time, an earlier attempt was aborted when a member of the party suffered a medical emergency, and the expedition had to turn back for shore. Read that carefully, because it is not a story about bad weather or equipment failure. A person on board got ill, and the correct medical response was to reach a hospital. And reaching a hospital meant abandoning the entire expedition and steaming for days. There is no ambulance, there is no evacuation. Illness that would be an inconvenience in any city or an afternoon of helicopter time in the North Sea becomes an expedition-ending event in the South Pacific Gyre because the only treatment available is transit. Brown returned, and by press reports from 2024, reached the coordinates with his son among the party, aboard a chartered expedition vessel. The details of the visit were reported in newspapers rather than in any formal record, so the precise dates and arrangements should be treated as press-sourced. What is not in doubt is the shape of the achievement. Getting to Point Nemo in the 21st century still requires chartering a ship, accepting weeks at sea, and going without any safety net at all. That is the same deal Polynesian navigators declined to take, for the same reason, with better hardware. Go back to that aborted attempt for a moment because the phrase "no evacuation" hides what actually happens to a sick person out there. Ships at sea are not without medical capability. Merchant vessels carry a regulated medical chest with a defined list of drugs and equipment, and an officer trained to a basic standard in using it. Radio medical advice services have existed for a century, and a captain anywhere in the world can reach a doctor ashore, describe symptoms, and receive instructions. The International Service in Rome has been giving free medical advice to ships by radio since the 1930s. On a well-run expedition vessel, there may be a doctor aboard and a proper stock of equipment. All of that changes the odds on the treatable cases. None of it touches the cases that need an operating theater. The closest comparable environment is Antarctica in winter, and the record there is instructive because the isolation is seasonal rather than permanent. In 1961, at the Soviet Novolazarevskaya station, the expedition's only physician, Leonid Rogozov, developed appendicitis with no possibility of flying out and no other surgeon within reach. He operated on himself, under local anesthetic, with 2 colleagues holding a mirror and handing him instruments, and he survived. In 1999, Jerry Nielsen, the doctor at the Amundsen Scott South Pole Station, discovered a lump in her own breast during the winter, when the temperature makes flying to the pole essentially impossible. A cargo aircraft made a midwinter airdrop of medical supplies so she could biopsy herself and begin treating herself with chemotherapy, and she was evacuated only months later, in October, once conditions allowed an aircraft to land. Those 2 cases are famous precisely because they are the exceptions where improvisation worked, and both of them happened at fixed stations with the resources of national programs behind them, on a continent with airstrips and an established, if seasonal, flight capability. At Point Nemo, there is no station, no airstrip, no seasonal window, and no aircraft that can drop anything with useful accuracy after a transit of that length. The improvisation available to a crew is limited to what is in the ship's locker, and whatever a doctor on a satellite call can talk them through. Everything else is transit, days of it, in a sea state you do not control, with the patient in a bunk in a moving vessel while the ship burns fuel it may need. That is why an expedition turns around. Not panic, not fragility. A calculation that the only treatment available is a hospital, and that the hospital is a week away and getting further with every hour spent continuing outbound. The same calculation, applied to machinery instead of bodies, is what makes the attrition rates in this water so stark. Take the fleets that have actually raced through the Southern Ocean and count how many finished. In the 1996 to 1997 Vendée Globe, 16 boats started and 6 completed the course. In the 2018 Golden Globe race, the retro technology event Abhilash Tomi was sailing, 18 boats started and 5 finished. Those are not failures of preparation. They are the outcome of sending small vessels into water where a single component failure has no repair path, because there is no port to divert to, no chandlery, no crane, no welder, and no spare mast within 5,000 kilometers. Ashore, a broken rudder bearing is an afternoon. At 48 degrees south, a broken rudder bearing is the end of the voyage, and possibly the end of the boat, because the crew now has to steer a vessel with compromised control through a sea that punishes any loss of directional stability for as long as it takes to reach somewhere. Distance turns a manageable mechanical failure into a survival problem. That sentence is the operational definition of remoteness, and it is the reason experienced sailors treat the region with a caution that looks excessive from a desk. The 1996 to 1997 race also produced the loss that hangs over this part of the ocean, and it happened in the South Pacific. Not far in oceanic terms from the region this story keeps circling. Jerry Roofs was a Canadian sailor, an experienced competitor, running second in the Vendée Globe in early January 1997 in an enormous South Pacific Sea. His position report stopped on 7 January. Conditions in that sector at the time were severe, with other competitors in the same weather reporting waves they described as the largest they had encountered. Race organizers alerted vessels in the region. Competitors diverted to search sailing patterns across the area of his last known position in the same storm system that had presumably taken him. With the same visibility problem that defeats every search out there, from a small boat in a huge swell, you can see almost nothing. No trace was found. There was no distress signal that resolved the question, and no confirmed transmission established what happened aboard. The available evidence never produced a definitive sequence, and the loss was recorded without an explanation. 6 months later, in July 1997, wreckage identified as his boat washed ashore on the coast of Chile, thousands of kilometers downwind and down current from where he had last reported. That is the only physical evidence the ocean returned, and it took half a year and the entire width of the South Pacific to deliver it. The drift line matters because it is the same circulation that defines everything here. The Antarctic circumpolar current and the westerlies move surface objects east and north out of the Southern Ocean and up along the South American coast. Anything lost in that water does not stay where it was lost. It is carried thousands of kilometers over months, which is precisely why searching for it near the last known position stops making sense within days, and why the debris on the seafloor at Point Nemo is the only human material out there that stays put. There is one modern case that appears at first to contradict everything above, and it is worth confronting directly, because the way it fails to contradict it is the most revealing thing in the record. On 30th November 2020, during the Vendée Globe, the French sailor Kevin Escoffier was sailing a 60-foot foiling monohull, confusingly also named PRB, several hundred nautical miles southwest of Cape Town in a big following sea. The boat came off a wave and the hull structure failed. His own description afterwards was that the bow folded at around 90 degrees and the boat effectively broke in two. He had time to send a single short message to his team saying he was sinking and that it was not a joke, and to get into a survival suit and a life raft. The boat went down in minutes. His electronics went with it. The rescue that followed is the fastest meaningful recovery ever achieved that far out in the Southern Ocean, and the reason for it is uncomfortable. Jean Le Cam, a 61-year-old French sailor with decades in the event, was about 8 nautical miles away. Race direction in France, watching the fleet's position telemetry and receiving the distress alert, diverted him immediately, along with 3 other competitors, Boris Herrmann, Yannick Bestaven, and Sébastien Simon. 4 boats converging on a life raft in the Southern Ocean, in fading light. Le Cam reached the position first and actually saw Escoffier briefly, then lost him. That detail should be underlined because it is the same visibility problem that swallowed the search for John Fisher. A life raft in a swell is invisible for most of every wave cycle, and a person aboard it can see a mast a mile away and be unable to attract attention. Night fell. The 4 boats set up a search pattern, coordinated remotely by race direction using position data, and continued for hours. LeCam found him again after around 11.5 hours and got him aboard in the dark, alone, from a life raft, in the Southern Ocean at 61 years old. Every commentator called it a miracle. It was not. It was a density problem with an unusual answer. Escoffier survived because the accident happened at a moment when 4 highly capable vessels, all fitted with satellite tracking, all in continuous contact with a control room, were inside a radius of a few dozen miles. That is a concentration of shipping, which that part of the ocean sees for perhaps a few weeks every 4 years, and only because a race puts it there. Line the cases up, and the pattern is not ambiguous. Dinelli in 1996 was saved by a competitor and an airdropped raft. Bullimore and Dubois in 1997 were saved by a warship after 4 days. Odyssey in 1999 was saved by a competitor. Tommy in 2018 was saved by a patrol vessel from a French island research station and reached 3 days later. Escoffier in 2020 was saved in 11 hours by a competitor 8 miles away. Jerry Roofs, alone in the South Pacific in 1997 with the nearest competitors hundreds of miles away in the same storm, was never found. Fisher in 2018 in the same ocean with no competitor and no ship and no island within reach, was not saved at all. The variable that determines survival in every one of those cases is not the quality of the equipment, the skill of the sailor, or the speed of the alert. It is the number of human beings who happen to be within a few hours' travel. That is the entire equation, and Point Nemo is defined as the place on Earth where that number is smallest. It also explains the strange asymmetry with the space program, which has been running in the background of this whole story, and now needs closing out because the same emptiness that makes rescue impossible is precisely what makes disposal attractive. And the reason space agencies care so much is that the alternative has been demonstrated repeatedly. When a large object comes down without control, the impact point is a lottery drawn from the entire band of latitudes its orbit crosses. The world is roughly 70% water, so the odds are good, and that is exactly the problem. Good odds are not the same as safety when the object weighs 20 tons, and the draw is repeated. The Chinese Long March 5B rocket made this argument for everyone. Unlike most large launchers, its enormous core stage reaches orbital velocity along with the payload. So after separation, there is a 20-odd-ton empty stage circling the Earth in a decaying orbit with no means of steering itself down. In May 2020, one of them came down over the Atlantic after passing directly over populated areas, and debris was subsequently reported on the ground in Côte d'Ivoire, including a pipe several meters long that damaged buildings in a village. In May 2021, another re-entered near the Maldives after a week of international attention and public speculation about where it would land. In July 2022, a third scattered debris over Malaysia and Indonesia, with fragments recovered on land in Borneo. In November 2022, a fourth came down over the Pacific. Nobody has been killed. So far, and by probability rather than by design. Space agencies that practice controlled disposal do so because they refuse to keep drawing from that lottery, and controlled disposal requires a target that is enormous, unpopulated, off all routes, and consistently available. There is exactly one such place, and it is the region around Point Nemo. Even then, the emptiness is never treated as absolute. Before any planned re-entry into the South Pacific Ocean uninhabited area, authorities issue navigational warnings to mariners and notices to airmen, defining the closure zone by coordinates and by time window, because the probability that a fishing vessel or a yacht or a research ship is inside a corridor 1,500 kilometers long is small, but not zero. The Volvo and Ocean Race fleets have sailed through that general region, while re-entries were in the schedule. Racers have joked about it publicly. Race organizers have not, because the responsible assumption is always that somebody is out there. There is the tension, in one sentence. We use Point Nemo as a target because nobody is there, and we still have to check whether anybody is there, and if anybody is there and something goes wrong, we cannot help them. There is one more consequence of the emptiness that has been building underneath this story since the beginning, and it changes the meaning of the debris field. Everything humanity has dropped into that ocean since 1971 is sitting in the most biologically inert deep water on the planet. In productive parts of the ocean, wreckage colonizes, steel corrodes, marine growth builds, sediment buries, and within decades a structure becomes part of the environment. In the abyssal South Pacific Gyre, with sediment accumulating at around a meter per million years, and microbial activity so low that oxygen penetrates the entire sediment column, burial and biological breakdown are effectively suspended. A titanium pressure vessel from a Progress freighter that hit the water in 1985 is lying on that seabed today in a condition much closer to how it landed than anything in shallower or richer water would be. We have created, without intending to, a preserved archaeological site of the early space age, 4 kilometers underwater, spread across thousands of square kilometers. In the water we are least equipped to visit. Mapping it would require a survey campaign comparable to a major deep-sea expedition, in a region with no port, no support, and no reason for a commercial operator to be there. The Nippon Foundation and GEPCO Seabed 2030 project has been driving a global effort to map the whole ocean floor. And the completed fraction of that map, assembled from actual soundings rather than satellite estimates, is still well under half the world's seabed. The blank areas cluster exactly where ships do not go. So the question that opened with Mir stays open. Nobody knows what the cemetery looks like. It is the only major human-made feature of the deep ocean that has never been imaged. And the reason is not that it is hidden. We know roughly where it is. We simply cannot afford or justify or safely conduct the trip to go and look. The other thing that has been changing quietly is the sea itself. And it is changing in the direction that makes the arithmetic worse. The Southern Ocean is where the planet's wind energy concentrates, and the belt of westerlies that drives it has been strengthening and shifting toward the pole over recent decades. The mechanism is well established. The ozone hole over Antarctica and rising greenhouse gas concentrations have both altered the temperature contrast between the polar atmosphere and the mid-latitudes. And that contrast is what sets the strength and position of the westerly belt. The index climate scientists use to track it has trended positive since the late 20th century, which in plain terms means the wind belt has tightened and moved south. Stronger, more persistent wind over the largest uninterrupted fetch on Earth produces exactly what you would expect. An analysis of more than 3 decades of satellite altimeter measurements, published in Science in 2019 by Ian Young and Agustinus Ribal, found that extreme wave heights in the Southern Ocean had increased measurably over the satellite record, by around 30 centimeters, roughly 5%, in the highest 10% of waves. 30 centimeters sounds trivial. It stops being trivial when it applies to the upper tail of the distribution, because the tail is where boats break. Shift the extremes of the world's biggest wave factory by 5%, and the worst days out there are worse than they were. When the sailors in these stories were learning their trade, and Southern Ocean swell does not stay in the Southern Ocean. Long-period waves generated in the westerly belt radiate outward across the entire Pacific, which is why beaches in California receive swell generated south of New Zealand. Point Nemo sits on the northern shoulder of that machine. Its own local winds are often moderate, because the gyre's high pressure suppresses them, and that is part of the trap. You can be sitting in 15 knots of wind under a clear sky and be lifted by a swell born in a storm nobody aboard will ever see, arriving from a system 2,000 kilometers away that never comes closer. The gyre itself is changing too. Warmer surface water is more buoyant and resists mixing with the cooler, nutrient-bearing water beneath it, which strengthens the stratification that starves the surface layer in the first place. Satellite ocean color records analyzed over the past 2 decades have indicated that the least productive waters of the subtropical gyres have been expanding, the ocean's deserts growing at their margins. Whatever the eventual magnitude, the direction is clear enough. The emptiness at the center of the South Pacific is not shrinking. That has a consequence nobody planned. The barren zone that keeps fishing fleets away, that keeps ships away, that guarantees no vessel of opportunity within 1,000 kilometers, is getting larger, at the same time that the waves at its southern edge are getting bigger. The system that makes the place dangerous is being reinforced from both ends. Ice is the third element, and it is the one that closes an earlier loop. The Antarctic ice that generated the sound recorded in 1997, the calving and cracking of enormous tabular bergs, is also the hazard that shapes every modern route through the South Pacific. Icebergs drift north from the continent into the shipping and racing latitudes, and while satellites can detect large bergs, growlers, and bergy bits, the smaller fragments broken off them are effectively invisible to both satellites and radar in a rough sea. A piece of ice the size of a car, floating almost awash, is enough to hole a racing yacht traveling at 25 knots. The response of the sport was to draw lines. Modern ocean races impose an ice exclusion zone, a boundary defined by waypoints and adjusted using satellite iceberg detection, which competitors are forbidden to cross. It is a real safety measure, and it works. It also compresses the fleet into a narrower corridor of ocean, forces boats to sail closer together on the same routing, and takes away the option of running further south to escape a system. That is the pattern that keeps repeating in this story, in every era. With every technology, ice detection removes one hazard and constrains the fleet's options. Better forecasting extends the operating season and puts more boats out in more months. Faster hulls cover more ground and take crews further from any coast in the same amount of time. Stronger communication makes a distress call instant and encourages routes that assume someone will hear it. Each improvement is genuine. Each one solves the thing it was built to solve, and each one nudges the accepted boundary of risk outward until the residual danger sits exactly where it always sat, in the gap between knowing and reaching. People keep going back anyway, and not out of recklessness. There are reasons, and the reasons have not changed. In early 2023, the Ocean Race sent its fleet on the longest leg in the event's 50-year history, from Cape Town to Itajaí, close to 13,000 nautical miles through the Southern Ocean, passing through the South Pacific and around Cape Horn. The boats were faster than the ones John Fisher sailed on, foiling monohulls capable of extraordinary speeds, with crews of 4 or 5 instead of 9. The routing again took them into the region of Point Nemo, again with the observation that the closest human beings for part of the leg were the crew of the International Space Station overhead. This time they were carrying instruments. The race ran a science program in which the boats collected data on the way through, measuring seawater temperature and salinity, dissolved carbon dioxide, and microplastic concentrations, and deploying drifting buoys for global ocean observing networks in areas where research vessels almost never operate. Racing yachts became sampling platforms in the one part of the ocean where sampling platforms do not exist. Stop on that for a second. The scientific community cannot easily get a research vessel to the South Pacific Gyre because the ship time is unaffordable and the transit is enormous. So when a group of racing boats decided to sail through it for sporting reasons, oceanographers strapped equipment to them, because a competitor's hull moving through that water at 20 knots is a better data-gathering opportunity than anything else on offer. The results included something the emptiest water on Earth was not supposed to contain. Microplastic particles were detected in samples taken in the remote South Pacific, in water thousands of kilometers from any coastline, any city, any river mouth, or any fishing fleet. The concentrations were low compared with coastal seas. They were not zero. It is the last reversal in the natural half of this story, and it fits the mechanism exactly. A gyre is a closed rotating system that concentrates whatever floats into its center. The same circulation that traps warm water and prevents nutrients from rising also gathers buoyant debris from an entire ocean basin and carries it inward, slowly, over years. The clearest, most sterile, least visited water on the planet is also a collection point, and it is collecting our rubbish from the surface at the same time that we deliberately deposit our spacecraft into it from above. Nobody planned that symmetry. It is simply what a gyre does, and it brings the story to the thing that is coming, which is larger than everything already down there put together. The International Space Station has been continuously inhabited since November 2000. It is a structure of around 420 tons, with a main truss more than 100 meters long and a pressurized volume comparable to a large aircraft, assembled in orbit across dozens of flights by 5 space agencies. Something in the order of 280 people from more than 20 countries have lived aboard it. It is the most expensive object ever built by human beings. It is also structurally aging. There have been persistent small air leaks in the Russian segment's transfer tunnel, tracked and patched and monitored for years. Its solar arrays have degraded and been augmented with new ones fitted over the originals. Its orbit decays continuously and has to be reboosted by visiting spacecraft. The partners have agreed to operate it to around 2030, and after that it has to come down. The alternatives were examined and discarded, and the reasons are instructive. Boosting it to a higher, long-lived orbit would require an enormous amount of propellant delivered in stages, and it would leave 400 tons of uncontrolled structure in a region where a collision would generate a debris cloud lasting centuries. Disassembling it and returning the modules would require a vehicle capable of carrying large pressurized sections back through re-entry, and no such vehicle exists or is planned. Handing it to a commercial operator was studied, and no operator wanted the liability of a structure with that age and that maintenance burden. That leaves a controlled deorbit, and the requirement is severe in a way that the mere operation only hints at. The station orbits at an inclination of 51.5 degrees, which means its ground track sweeps across almost every populated latitude on the planet, over the great majority of the world's population. An uncontrolled re-entry of a 400-ton structure would produce a debris footprint likely well over 1,000 kilometers long, with surviving mass estimated in the tens of tons. The dense components, the docking mechanisms, the gyroscopes, the propellant tanks, the thick truss fittings. Dropping that on a random point along a track that crosses Europe, Asia, and North America is not an acceptable risk to any of the agencies involved. So NASA and its partners committed to building a machine whose only purpose is to destroy the station. In June 2024, NASA awarded SpaceX a contract, reported at a value of up to around $843 million, to develop what is called the United States Deorbit Vehicle. As described publicly by NASA and SpaceX, it is derived from the Dragon spacecraft, but heavily modified. A Dragon capsule structure mated to a greatly extended trunk section, packed with propellant tanks and additional engines. The figures released describe something in the region of 46 Draco thrusters, more than 16 tons of propellant, and a total vehicle mass of roughly 30 tons, which would make it far larger than any Dragon ever flown. NASA will take ownership of the vehicle and operate it. The concept of operations reads like a slow, deliberate demolition. It launches roughly a year and a half before the end, docks with the station, and waits. In the meantime, the station's altitude is allowed to fall naturally, from its operating height near 400 kilometers down toward about 330, using atmospheric drag rather than propellant, which is free but slow and takes many months. The final crew departs at some point during that descent, and after they undock, the station becomes cargo rather than a habitat. No one aboard, systems maintained remotely. An empty structure the size of a football field falling gradually toward the atmosphere. Then the deorbit vehicle takes over. The final phase involves a series of burns over a period of days, culminating in a long final burn that sets the re-entry trajectory and the ground track, aimed so that the breakup occurs over the South Pacific and the debris corridor lies inside the uninhabited area. Breakup begins around 80 kilometers up. The solar arrays and radiators go first, then the truss, then the pressurized modules, in a sequence that engineers can model but cannot fully predict, which is precisely why the European Space Agency chartered aircraft to watch Jules Verne come apart in 2008 and why NASA has studied every previous large re-entry. The resulting footprint for a station this size is expected to run to well over 1,000 kilometers, potentially approaching 2,000, and the entire corridor has to fall in water with nothing in it. The target is Point Nemo. Take a step back and look at what that actually means, because it is the sharpest version of the contradiction that opened this story. Somewhere around 2030 or 2031, the largest object humans have ever assembled in space, an object that cost over $100 billion and housed people continuously for 3 decades, will be steered by a purpose-built robotic tug into the atmosphere and dropped, deliberately, with an accuracy measured in kilometers, onto the one part of the ocean that no ship visits, no aircraft can reach, no cable crosses, and no rescue service can serve. It will be the largest controlled re-entry ever attempted, executed with a precision that would be considered excellent for a missile test. And when it is over, nobody will go and look. There will be no survey vessel on station to record the impacts. No sonar mapping of the debris field afterwards. No recovery of a single fragment. No photograph of anything on the bottom. Whatever survives to the seafloor will join the accumulated wreckage of half a century of space operations, 4 kilometers down, in water so poor in life that the metal will sit there almost unchanged for a very long time. The most documented structure in the history of engineering will end as an unphotographed scatter of debris in an unsurveyed patch of abyssal plain. We will know where it is to within a few kilometers. We will never see it. That is not a failure of will or a lack of curiosity. It is the direct output of every mechanism this story has laid out, and by now the change should be visible in full. It starts with atmospheric circulation. A belt of high pressure sits over the South Pacific and forces air downward. The wind drives surface water inward, and the water piles into a slow rotating mound with nothing rising from beneath it. That single fact starves the surface of nutrients, which strips out the plankton, which removes the fish, which removes the fishing fleets, which removes the only reason a working vessel would ever be nearby. The clarity of that water, the clearest natural seawater ever measured, is a direct readout of the same emptiness. Geometry does the rest. The shortest routes between the ports that matter all curve away from that quadrant of the Pacific, so no merchant traffic passes through. No traffic means no cables, no repair ships, no bunkering, no ports, no infrastructure of any kind, and a hole in the position reporting systems that rescue centers depend on to find a ship near a casualty. On the map, the region is inside somebody's search and rescue area. In practice, there is nothing inside it to send. Then, the weather activates the trap. The westerlies encircling Antarctica have the longest uninterrupted fetch on Earth, and they deliver long-period swell into a region where there is no lee, no anchorage, no harbor, and no direction in which conditions improve. Water temperatures in the range of 5 to 10 degrees give a person in the sea a window measured in minutes for useful movement, and hours before the odds are gone, while the nearest capable ship is measured in days and the nearest hospital in weeks. Human motive supplies the exposure, and it always has. Competition puts racing fleets there because the westerlies are the fastest wind in the world. Research puts a drill ship there once in a generation because a proposal survived a decade of review. Ambition puts a chartered expedition vessel there because a coordinate on a chart is a thing some people need to stand on. Space agencies put hundreds of vehicles there because it is the only sufficiently empty target on the planet. Technology changes what those people can do, and it changes it unevenly, which is the part that keeps catching everyone out. Satellite navigation solved position absolutely. It did nothing about distance. Satellite communication solved the alert, and every case in this story confirms it. The signal always got through. And the signal was never the problem. Weather forecasting solved surprise in the strategic sense in sessions and sense, giving crews 2 or 3 days of warning about a developing system, and it cannot give a boat at 48 degrees south anywhere to go with that warning because there is nowhere to go. Hull design and materials made boats faster and stiffer, which means they cover more ocean and are therefore further from help at any given moment. And stiffer structures fail differently, sometimes suddenly, as Kevin Escoffier discovered when a hull that had been performing perfectly folded in a few seconds. Acoustic sensing reaches thousands of kilometers and cannot lift anyone out of the water. Satellite altimetry maps the shape of the seabed and cannot see anything smaller than a mountain. Every one of those is a real gain. Not one of them is a rescue. If you wanted to change that, the shape of the required effort is not mysterious, and the numbers explain why nobody has done it and nobody will. Consider what a genuine survey of the spacecraft cemetery would take. The water is around 4 kilometers deep, which puts roughly 400 atmospheres of pressure on anything you send down. So the vehicle has to be a full ocean-capable, remotely operated system, or an autonomous submersible rated for those depths, of which there are relatively few in the world, with schedules committed years in advance. It has to be carried on a vessel with dynamic positioning, deep-water winches, and enough endurance to stay at sea for months, of which there are also few, and all of them are expensive. Day rates for that class of vessel run into the tens of thousands of dollars before you add the equipment and the crew. Then there is the search itself. Deepwater sonar surveys map the bottom in swaths, and the width of the swath depends on the altitude of the sonar above the seabed and the resolution required. To find objects a few meters across, you have to fly low and slow, which narrows the swath to perhaps a couple of kilometers at best, at survey speeds of a few knots. A single debris corridor from one re-entry can be 1,500 kilometers long and 100 wide. That is on the order of 150,000 square kilometers for one event, and there have been hundreds of events over 50 years, with corridors overlapping in different orientations across an area larger than several European countries combined. At realistic survey rates, mapping even a fraction of that at object detection resolution is a multi-year campaign for a dedicated fleet, in water 2 weeks steaming from the nearest suitable port, with no shelter to run to if a southern ocean system comes through and no possibility of medical evacuation for anyone aboard. The search for one missing airliner in the southern Indian Ocean, an operation funded by governments under intense public pressure, covered a comparable order of magnitude of seabed over years and did not find the aircraft. The spacecraft cemetery has no families demanding answers and no legal obligation attached to it. It will not be searched. Now run the same exercise on rescue. To provide meaningful coverage at Point Nemo, you would need either a permanently stationed vessel with medical facilities, parked in the center of the South Pacific Gyre, doing nothing, resupplied by other ships making the same 2-week transit, or an airbase within 1,000 kilometers, which would require building a runway on an island that does not exist. There is no third option, because helicopters cannot fly that far, and long-range aircraft cannot pick anyone up. The cost of either approach, measured against a casualty rate of perhaps a handful of incidents per decade, is indefensible to any government on Earth. So the honest summary is that Point Nemo has no rescue capability, is not going to get one, and everyone who goes there knows it. That is not negligence. It is a rational allocation of finite resources made openly, and it is precisely why the risk sits where it does. Understand what that does to the psychology of the people who still go, because they are not gamblers. Look at the actual behavior in every incident here and you see the opposite of recklessness. Crews reducing sail before the worst of a system arrives. Skippers choosing storm tactics based on wave period and boat design. Race organizers drawing exclusion zones from satellite ice detection. Expedition leaders turning around and losing an entire venture because one person aboard fell ill. Sailors carrying sealed beacons they hope never to open. A drilling program spending years of review before committing a ship. A space agency spending $800 million on a vehicle whose only job is to make sure a controlled re-entry stays controlled. The people involved are not underestimating the place. They are pricing it accurately and accepting the price because the alternative is not going at all. That acceptance is the through line from the very beginning. Polynesian navigators priced the emptiness and declined, correctly, because their entire method depended on land generating signals, and there were no signals to read. They were not defeated by it. They simply recognized it as the one region their system could not serve, and stayed at its edges, on Rapa Nui and Pitcairn and Henderson, islands that sit on the rim of the void. Every subsequent era has priced the same emptiness with better instruments and reached the same conclusion in a different form. It can be crossed, it cannot be inhabited, and it cannot be defended against. What changed is not the ocean. It is the reasons for being there. The gyre no longer has to offer fish or trade or land to draw people in. It draws them now because it offers absence, and absence has become a resource. It is the only place on Earth big enough and empty enough to put things we cannot safely put anywhere else. It is where the space age goes to be disposed of, and by the arithmetic of the coming decade, it is where the largest and most complex machine humanity has ever built will be deliberately destroyed. There is a version of the future where that changes. Autonomous underwater vehicles are getting cheaper and can be launched in swarms. Uncrewed surface vessels can now cross oceans on solar and wave power and stay out for months, and some of them are already surveying remote water at a fraction of the cost of a crewed ship. If any survey of the cemetery ever happens, it will be done by machines, working slowly, without anyone aboard, because the constraint was never technological curiosity. It was always the cost of keeping human beings alive out there, which returns the story to where it began, and to the only fair answer to the question it started with. We can drop 143 tons of space station within a few kilometers of Point Nemo because the delivery problem is a problem of physics and trajectory, and physics does not need to eat or breathe or be brought home. Aim, burn, release, done. The object does not care that it takes 2 weeks to reach the impact site. It is never coming back. A human being at the same coordinates carries an entire support system with them, and every element of that system has a clock attached. Air is free. Fresh water has to be made using fuel. Food runs out. Warmth requires energy. Injuries require treatment. Fatigue accumulates and cannot be repaid at sea. Every one of those clocks runs on supplies that came from a port thousands of kilometers away, and none of them can be topped up out there, because there is no out there to top them up from. And that, stripped down, is the answer. Precision is cheap and reach is expensive. And at Point Nemo, the gap between them is the widest it gets anywhere on the surface of this planet. There is one detail about the coming re-entry that almost nobody thinks about, and it is the most human part of the whole operation. At some point in the early 2030s, a small group of people will leave the International Space Station for the last time. They will do the things crews always do before undocking. Transfer the last samples, close valves, secure hatches, run through a checklist that somebody on the ground wrote years in advance. There will be a final photograph. Then the hatch closes, the latches release, and the spacecraft backs away. For the first time since November 2000, there will be nobody aboard. The lights will still be on. The air will still be circulating. The station will continue orbiting, empty, at 8 kilometers a second for months, slowly losing altitude to a thin wisp of atmosphere that barely qualifies as air. While flight controllers in Houston and Moscow keep its systems alive by radio and the deorbit vehicle sits docked to the front of it, waiting. On the surface of the ocean it is aimed at, absolutely nothing will change. The gyre will keep turning, driven by the same descending air and the same wind stress that have been driving it for millions of years. Long swell from a storm somewhere south of the 50s will keep crossing that water, rising and falling on a 15-second beat, with nothing in its path for 2,500 kilometers. The surface layer will stay warm, transparent, and starved, and light will drive down into it further than into any other water on Earth. 4 kilometers below, a millimeter of new sediment will take another 1,000 years to settle onto a bed of debris that has never been photographed. Some weeks before the re-entry, a bulletin will be published in the routine format that maritime authorities have used for decades. A navigational warning defining a closure area by latitude and longitude, with a start time and an end time, advising mariners to avoid the region because of the planned re-entry of a space object. It will be transmitted by satellite text and radio into every ship's bridge in the South Pacific. Aviation authorities will issue an equivalent notice, rerouting the small number of long-haul flights that cross the Southern Pacific. Almost no one will need it. Emptiness is why the place was chosen. The warnings will go out anyway, because the probability of a vessel being inside a corridor that size is not zero, and because if a vessel is inside it, nobody can get them out. If anyone were there, the view would be extraordinary and brief. In the last minutes, a point of light in the west, brighter than any star, moving faster than an aircraft, splitting into 2, then 5, then dozens of separate burning fragments trailing smoke across the sky, each one with its own color and its own decay rate. The whole formation stretched across the horizon and taking several minutes to pass. Then, a long silence, and minutes later, distant impacts across an area larger than most countries, unheard and unseen from any single point. Nobody will be there to see it. It will be recorded by tracking radars, by satellites, possibly by an aircraft chartered to observe the breakup the way the Europeans observed Jules Verne in 2008, flying from Tahiti or Chile with spectrographs pointed at the sky, gathering data because computer models of how large structures come apart are still not good enough to be trusted on their own. And then the ocean closes over it and the operation ends, and the file is complete, and nothing further will ever be learned about what happened below the waterline. That is what makes this place different from every other dangerous region on the planet. A mountain kills you with altitude and cold, and you can still walk to the base of it and look up. A desert kills you with heat and distance, and you can still drive to its edge. Point Nemo does not kill anybody, because almost nobody ever gets close enough to be killed. It simply removes the possibility of being helped. And it does so with a completeness that no other environment achieves, using nothing but geometry. The conditions that produce it are not going away. The high-pressure cell over the South Pacific is a permanent feature of atmospheric circulation. The westerlies will keep running around the bottom of the world with nothing in their way. And by the satellite record, they are running slightly harder than they were 30 years ago. The routes will keep bending away because ships follow money and there is no money there. The absence of fish, the absence of cables, the absence of ports, the absence of aircraft with the range to reach it, all of that is structural, and none of it is a problem anyone is going to solve, because solving it would cost more than the entire history of activity in that region has been worth. People will keep going. A race fleet will pass through in a few years, faster than the last one. Heading near Fimbestiberkasturidos, carrying scientific instruments because it is the only way anyone gets data from that water. A research vessel will cross it once in a while on a transit between two other things, because the ship time can only be justified as part of a longer voyage. Someone with money and a reason will charter an expedition boat and stand on the deck at 48 degrees 52.6 minutes south, 123 degrees 23.6 minutes west, and look at water that is identical in every direction, and know that the nearest other human being might be in orbit. And in a control room, somewhere, on a screen, a line will be drawn across that water. It will look like the routine product of a competent organization: a projected ground track over a chart of the South Pacific, a shaded ellipse for the debris footprint, a countdown clock, and a set of numbers in a corner giving the predicted breakup altitude and the coordinates of the aim point. Engineers will watch it and check it against telemetry. The corridor will be a long, narrow oval lying across a region of the chart with no ports, no soundings, no cables, no traffic, and no names on it. Beneath the oval, 4 kilometers down, there is a floor that no camera has ever reached, carrying the wreckage of half a century of spaceflight, in water so lifeless that the metal is barely changing. We know where it lies to within a few kilometers. We have never seen it, and after the largest controlled re-entry in history puts 400 more tons onto it, we still will not. The screen will show the corridor. The ocean will show nothing at all.